Uh, Hi, I'm Rohan. As Lee said, I'm an 11th grader at Lynbrook High School in San Jose, so I'm from the South Bay. I think this is my third talk. I gave a talk earlier this year at PyCon, and then I gave one at PyGotham in July. So this is my third talk at PyData SF. Wait, are those slides? Oh, sorry. Can you hear me in the back? Okay, great. So we'll just wait for the projector to get set up. Like this? Okay. All right. Okay. Looks like we're ready. So, I'm Rohan. I'm an 11th grader at Lynbrook High School, and I really like programming in Python because, well, I started like if you saw the keynote, I started because it was easy, and I'm staying because of the community. So the community has been really helpful, and I've gotten a lot of great suggestions from people about improving my projects and stuff. So thank you for that. So my talk is titled Machine Learning versus the Flu. So my project is about using machine learning to try and predict on how influenza virus strains will mutate in the coming years based on how they've mutated in previous years. And my talk will cover the process that I went through to do this project, as well as the libraries and the challenges that I faced getting there. So I've pretty much covered this. I'm going to be in 11th grade this fall. I've been programming since 8th grade, and I like bioinformatics, machine learning, and data analytics. So let's first start out with the problem that I was trying to solve, and that is the influenza. So chances are you've probably had the influenza in previous years, and we take a vaccine every year so we can try and gain immunity from it. But right now, current methods of creating vaccines for the flu aren't the best, because scientists just vote on what antibodies and what drugs should go into the vaccine, and this practice has been called questionable by the National Institutes of Medicine, which is not that great if you don't want to fall sick. And sometimes the vaccines don't work for every strain. So if you remember, in 2009, there was a worldwide H1N1 pandemic, and that year the flu vaccines did not match what the flu strains looked like for that year. So a lot of people fell sick that year. And it was the largest global pandemic since the 1918 Spanish flu towards the end of World War I. So it was pretty big. So my goal was to create a more effective way to create vaccines. And by doing that, I wanted to predict how the flu itself would look like in the coming years, so that scientists could analyze that and see, based on what that flu strain would look like, to use that data and come up with a vaccine for that, since vaccines are just weakened versions of the flu strains themselves. So to understand how to create vaccines for the flu, we have to look at how the flu would infect a host cell. So I'll just go off the podium here. So if we look at the first picture, the little yellow blob with the purple dots around it, that's a virus, and the big orange blob is a cell. So look at those little purple dots around the virus. Those are called surface proteins, and they regulate entry and exit of the virus in and out of the cell. So in the second picture, you have the virus entering the cell because the surface proteins have binded to those receptors on the cell membrane, and the virus has injected its viral DNA and RNA into the cell. Next, in picture 3, as the cell grows, the virus's genetic material as well as those surface proteins also grow. And as the cell is about to die, the viruses recombine and they exit the cell and go on to affect more cells in your body. So what I learned from this was to target those little purple dots, so those surface proteins. In the flu, they're called hemagglutinin and neuraminidase, but for simplicity's sake, let's just call them HA and NA, because biologists just really love super long names. So what I decided to do was, instead of trying to predict what the flu's genetic material would look like, so instead of those little red squiggly lines, I would just predict how the surface proteins themselves would look like. So if I could possibly take those out or try and predict what they would look like in the coming years, then scientists can create weakened versions of the flu with those same surface proteins, so HA and NA, and then the white blood cells in your body would know what the virus's surface proteins would look like and be prepared for when the real flu attacks. So my overall approach for this project was to obviously predict future genetic sequences of the flu so that scientists can create vaccines for that. And by doing this, I would obviously have to use machine learning. And I also looked at phylogenetics. Phylogenetics, which is the study of relationships between individuals on an evolutionary tree. So just looking at the relationships between grandparents, parents, and children, like so. So you've probably seen one of these from your biology class in high school. Here we have a toy evolutionary tree of the flu. Obviously, those sequences are not that simple. They're actually 1,700 letters long. I've just shortened them down to 4 base pairs for simplicity's sake. So if we look, let's look at the bottom part. So we have H, G, F, and E. So H is a great-grandparent, G is a grandparent, F is a parent, E is a child. So what I wanted my machine learning algorithm to understand was how G has changed from H, how F has changed from G, and how E has changed from F. So if you notice, H has a genetic sequence of AAA, G has a genetic sequence of AAAT, F has a genetic sequence of AAAG, and E has a genetic sequence of AAAC. So I wanted my machine learning algorithm to learn how they have changed over the years, and then predict based on that information how the child E, what the child of E would look like. So in this case, we can reasonably infer that it is most likely that the 4th base pair, or the last base pair, would probably change for the child of E. So perhaps AAAA or AAAT. So this was my setup. So my plan of attack to do this project. So first was to obtain data from the IRDB, or Influenza Research Database. This is a database funded by the National Institutes of Health with a lot of useful data about flu strains, such as the flu strain itself, the organism ID, as well as where it was found, and the specifics of the person it was found in, like the age and gender. And next was to read in the genetic sequence of HA and NA, and then train a machine learning model based on the evolutionary relationship, so how the grandparent and how the parent has changed from the grandparent, and how the child has changed from the parent. So using that data to predict on what the child of the child would look like, and then I would evaluate, I wasn't sure yet, but I would evaluate accuracy some way or another. But I quickly ran into some problems, because this was last year, and I was still kind of a newbie to this whole machine learning in Python thing. So I thought I would have to write my own machine learning algorithm myself. So I wasn't sure how accurate that would be, because I had never written one before. I also wasn't sure what kind of machine learning algorithm to use, because I was inundated with all this information, neural networks, decision trees. What does that even mean? I wasn't sure how to measure accuracy and how to read in a FASTA file, which was the file format that those genetic sequences of HA and NA were in. So I wasn't sure how to read those in. So this was where my first library helped me. So this is called Biopython. So Biopython is just a Python library dealing with anything with biological data. So it helps with, so Biopython specifically helped me with reading in that FASTA file, because there's a little module in Biopython called seq.io, seq.io, which is used for input and output with specific biological data, because I quickly found that FASTAs wasn't the only file format that I used. I used FASTAs, I used GenBank, which is another which is another file format for holding genetic sequences, as well as UniProt data. So Biopython helped me with all of those things. So once I got past that initial hurdle, I had to get to the flu prediction algorithm itself. So the good stuff where I actually predicted what next year's or next flu season's flu strain would be. So I did some background research, and I decided that a decision tree based algorithm, so like a gradient boosting algorithm or decision tree or random forest algorithm, would be the best fit, because a phylogenetic tree is similar to a decision tree. As you saw earlier, the phylogenetic tree has branches where the child or brothers branch off from the main tree, and a decision tree similarly has nodes asking certain questions with branching off based on the different answers. So I went on to write a simple decision tree classifier, because I also in part chose decision trees because it would be easy for me to debug, because I thought I had not learned calculus, and I don't think I could have done a neural network. So there are a lot of problems. So first off, it was only a classification algorithm, and I would have preferred a regression algorithm, and it often underfit my data. So my algorithm was too simple for the really complex flu data. So it had really bad prediction accuracy, and it underfit my data. So this is where scikit-learn helped me. So I learned about scikit-learn while I was doing this project, and you've probably heard of scikit-learn, the Python machine learning library. So this helped me in two ways, because first of all, I was on a bit of a deadline, because I wanted to submit this for a science fair, and writing that whole decision tree algorithm took a lot of time. So say I wrote my decision tree algorithm, and I decided maybe this wasn't the best, and I wanted to write some other sort of machine learning algorithm. That would also take some more time away from my project, which I could be doing more background data about the biology side of this. But instead, if I could use scikit-learn instead, and if I could quickly, not only were the models good, I could also quickly swap out one for another. So maybe if I didn't like X model, then I could try this another model, Y, and import it. And it would be really easy for me to just try out all these different models and see which one was the best. So this was my updated setup with all the Python libraries, as well as my background research. So the first step stayed the same. I would still obtain data from the IRDB. The second step I changed because of Biopython. So I would read in the genetic sequence of the flu using Biopython. And I had to add a third step, which is encoding the data. So scikit-learn only takes numerical input, so I had to change the biological data, which is in combinations of A's, T's, G's, and C's into numerical data. And then I would train a machine learning model on the parent-child relationships between flu strains, and then I would evaluate the accuracy using cross-validation and R-squared score. So this is just a whole overview of my algorithm in a picture that I drew. So I would create a phylogeny tree, encode the data, give the data to my machine learning model, predict sequences, test the accuracy, and then add more data and see how if my accuracy got any better. So this was how easy it was to read in a FASTA file with Biopython. So previously, I was reading it in as a normal TXT, which was a real pain to try and understand where the flu strain itself was. So right here is a FASTA file containing 100 HA strains. So just using one line, I can put them all in a list for the scikit-learn to predict on. And so this was my encoding method, where I turned all the letters of A's, T's, G's, and C's into numbers. So I corresponded 1 to A, 2 to T, 3 to G, and 4 to C. So I first changed all the letters to numbers, and then I broke up the entire genetic sequence into chunks of 15. So into chunks of 15, and I put those all in one big list. So each list would have every element in the list would have a number with 15 digits, and there would be roughly 80 80 elements in each list. So roughly 1,700 numbers long would be the entire list with every element. So this was my decision tree algorithm before scikit-learn, and this was my decision tree algorithm after scikit-learn. So I didn't expect you guys to read this. So this was how easy it was to read to use a scikit-learn random forest algorithm, which I ended up using later. In that first block of 3 lines, I am reading in, I am importing the library, and then in the last 3 lines, I'm computing the cross-validation accuracy. So this is how cross-validation, on 80% of the data I trained, and then on the remaining 20%, I did the prediction and I evaluated the accuracy. And I also used R² score to evaluate how accurate my algorithm was. While Biopython and scikit-learn were really great, there were some drawbacks, because in my previous algorithm, I was using the grandparent-parent-child relationship. So 3 generations of flu data would be the training data for my machine learning algorithm to predict on. But with scikit-learn, I could only go 2 generations from parent to child. So I wish I could have added that extra generation, which have probably boosted my accuracy a bit. Also, scikit-learn couldn't take any letters or characters, and also couldn't hold that many significant digits. So let's move on to my results. So I trained on 2 flu subtypes, H1N1 and H3N2. So this is H1N1 cross-validation scores. Just a bit of background, H1N1, or more commonly known as the swine flu, this was the one which caused the big 2009 pandemic. And as you'll see, these scores were generally a bit lower than H3N2, because H1N1, although it does not infect humans as much as H3N2, it's much more virulent or dangerous because it mutates a lot faster. So at the bottom are my 3 algorithms which I use: decision trees, random forests, and extra trees. This is my cross-validation scores for H3N2, which is H3N2 more commonly affects humans, but it's not as dangerous because it doesn't mutate as rapidly as H1N1. So these are the R² scores for H1N1, as well as the R² scores for H3N2. So as you can see, random forest is performing the best in pretty much all the metrics in both of the flu subtypes, and I'll explain why in a bit. So these are all of the scores, and this is my comparison to other studies. So the 2 bar graphs you see on the left, on your left, those are 2 European studies. So the one on the very left is a German, and the one in the middle, I believe, is from Spain. So these are both formula-based approaches. So they just came up with a formula, and then based on that, they were predicting the flu sequences. And my algorithm is on the very right, where I'm using machine learning. And as you can see, the results look very promising.
Can you say briefly what was the difference in the strategies that was used by the other 2 predictions?
Oh, those were formula-based approaches. So yeah. So now let's move on to why I think a random forest perform the best. So it helps with a little bit of background on the 2 types of flu mutations. So you have antigenic drift and antigenic shift. So the main difference is that drift changes are the smaller changes, and the shift changes are the really big changes. So if we look on the leftmost side, we have a flu mutation. So again, those little purple dots, those are the surface proteins, so HA and NA. So these drift changes happen quite often. They're smaller changes, so less replication errors and less mutations. And these are the more common types of flu mutations. So as you can see, those surface proteins, they've just altered a little bit from one generation to the next generation. Whereas if you look at antigenic shift on your right side, you see a lot of different flu strains have combined to create one super dangerous flu strain. So just as an example, let's say the one with the orange dots, that flu tends to infect people in tropical climates. The purple one affects people in temperate climates, and the green one affects people in cooler or colder climates. So you see all of those have combined their surface proteins into one new flu strain. So that new flu strain can infect people in any climate, making it really easy to enter the host cell no matter what type of weather that they live in. So this flu strain this type of mutation can be especially dangerous, although it does not happen as much. So an ideal algorithm would probably put those drift mutations at a higher priority because they happen more often, whereas those shift changes should be less of a priority but still taken into account because they can cause massive outbreaks like in 2009. So why I think random forest performed the best was because it created an ensemble of trees which lowered the variance, which gave less importance to the shift changes. So what I think decision trees was doing was it can tend to create over complex trees which overfit the data. So it was giving too much importance to those shift changes, which was not good as they do not happen that much and can overgeneralize the data. So random forest with its random splits and generally weaker trees was able to pick up those, was able to give less importance to those shift changes because the real strength in random forest is averaging out all the trees' outcomes together, which generally creates for a stronger model. And I think extra trees gave too little importance to the shift changes because they are still to be taken into account, but I think extra trees did not give any importance to those shift changes at all. So in sum, I wanted to create a better mechanism to create influenza vaccines, and I used Biopython and scikit-learn to simplify my data analyses and also help me improve my accuracy. And the results look very encouraging, and I am continuing this work with researchers on the East Coast, and now I'll take any questions as well as suggestions because I'm obviously not, I'm still new to this whole Python machine learning, so any input that you have is greatly appreciated, and you can see this project at this link. So thank you very much. Yeah. Oh, X and Y. So X would be the parent flu strain, and Y would be the child flu strain.
So is it basically X will be a number between 1, 2, 3, 4, and then Y is between 1, 2, 3, 4?
Yeah, yeah.
Okay. So this is a comment, but I think you should be using a multi-class classification instead of regression.
Okay.
So because you're assuming the difference between 1 and 2 is the same as the difference between 3, which also needs to be the case.
Okay. Okay, thanks. Yeah?
Have you looked at proteins? So you mentioned that you looked at intro, which is like database, because like typically like genetic, like whatever's in the gene is not necessarily translated into a protein. So have you taken that into consideration?
Yeah, the HA and NA, those are proteins themselves. They're not genes.
Right, but genes are not. So you took the genetic sequence, though, right?
Yeah.
Which is the gene itself. So it doesn't get translated into, like, not all the gene is translated into a protein. It's like, right, like, what you saying?
Oh yeah, like I was that's one thing I'm trying to do is instead of splitting it by 15, just split it into 3s instead. Is that what you're saying?
Yeah, and
To do an amino acid.
Like that.
also like shift it too, because like they have like different reading frames.
Yeah. Okay, yeah, I think I'll do that. So instead of splitting it into 15s, I just went with 15 because that was the most significant digits that a Python float could hold, so I just went with that earlier. But I think I'll start splitting it into group like threes, which code like those specific codons for those specific amino acids. Yeah.
And then you can also put into your data set, like, for example, like, I don't know if they curated these proteins, but some locations of the proteins themselves are not as important as other locations. So, for example, on the receptor, like the surface would obviously matter a lot.
Yeah.
Like the membrane ones.
Yeah.
You can like try to add that into your data set to see if that helps.
Okay. Yeah. Yeah, that's what I'm working on right now is trying integrating gradient boosting. Like I've tried XGBoost as well as scikit-learn gradient boosting. So I'm working on that like right now because this was during school. This was during the school year, so I didn't have much time. So I've been working on that during the summer, like right now. Which one? Okay. Okay, thanks. Yeah.
So you're doing comparisons against the studies from 2009, now 7 years later. The prediction strategies that are being used today better or incorporate?
Wait, are you looking at these two studies?
Yeah.
Oh, well, with the...
So I guess, let me reframe the question. This is exciting, right? That
Yeah.
a teenager can produce better results than like the global influenza scientific community. That's fabulous. So has the global scientific influenza community adjusted their prediction strategy?
I think they are starting to move towards machine learning. Like with the researchers that I'm contacting on the East Coast, they haven't fully caught up with the machine learning strategies yet. So I'm trying to work with him to somehow use the formula based approaches up to some point, and then based like right now it's at 90, roughly 85, 90 something percent. So those right now those other formula based approaches, they're also getting, like as you can see, the one to the far left, it goes all the way up to 93 for H3N2. So what I was thinking of doing was use those formula based approaches, and then for that extra 7% to get to 100%, maybe use machine learning for that instead of using machine learning from the base and then going as far as I can using the formula based approaches, and then on top of that using that existing framework and then building machine learning on top of that.
All right, well, thank you so much, Rohan. Let's give him one more round.